we are honored to host Dr. Kana M Sureshan, exploring a wide range of topics from cutting-edge discoveries to the challenges faced by scientists today. Our host, Mr. V. Shivakumar, will be delving deep into Dr. Sureshan's groundbreaking research, innovative ideas, and their potential impact on our world.
Professor Dr. Kana M Sureshan, Dean of Infrastructure and Planning at the Indian Institute of Science, Education and Research, IISER, Thiruvananthapuram. He is a professor in chemistry with a PhD from the National Chemical Laboratory in Pune. He is a recipient of Technology Innovation Award of the Ministry of Chemicals and Fertilizers, Government of India, and several fellowships, including the Ramanujan Fellowship, Swarna Jayanti Fellowship of the Department of Science and Technology, and the Alexander von Humboldt Fellowship of Germany, JSPS Japan Fellowship, among many other fellowships. He was elected Fellow of Indian Academy of Sciences in 2020 and has worked as a postdoctoral fellow in Max Planck Institute for Molecular Physiology and as a senior scientist, Institute of Life Sciences, Hyderabad. He has 8 patents to his name and has published over 125 research papers in various international journals. Welcome, Professor Kana Sureshan. Tell us about your interest in science and how did you overcome the challenges you faced initially when you got into science?
I was very much interested in observing things initially when I was a young student. I always had this curiosity how things works and all. Fortunately, I got good marks in plus 2. It was a vocational higher secondary school system. I was the first rank holder in the state. Then I joined BSc Chemistry in Pioneer College in Kannur district. Then again, SN College in Kannur, I did MSc there. And I cleared CSIR actually. I'm one among the 3 candidates from Kerala who cleared CSIR at that time. And with the help of my seniors, I went to National Chemical Laboratory. From there on, I understood more things about science and how one can design things and how we can make materials and all those things.
You did your PhD in the National Chemical Laboratory. What was your PhD on?
My PhD was on some specific molecules called inositol. Inositol phosphates are signaling molecules in our body, so which is involved in calcium signaling basically. I was making derivatives of these molecules for their biological studies.
So after Pune, you moved to Japan?
Yes, I moved to Japan as a JSPS fellow. JSPS is a very prestigious fellowship by the Japanese government. So I went to Matsuyama, actually Hime University. Again, I worked on inositol phosphate signaling system there with Professor Yutaka Watanabe. Here I did carbohydrate chemistry in India. Then I learned phosphate chemistry. From there I went to UK actually later. Because one Professor Barry Potter from UK, he came and he met me in a conference in Japan. He said he wanted me there in his group as a research officer. He invited me and I did there some nucleoside chemistry, nucleoside and nucleotides. Then I went to Germany after that as a Humboldt Fellow in Max Planck Institute for Molecular Physiology, it is in Dortmund, where I did chemical biology. So basically using chemicals for addressing biological problems. Then I came back to India.
So it was some kind of a multidisciplinary move for you from chemistry then to biology.
I am very much interested in biology, especially chemical biology, cellular signal transduction, for example. We wanted to do these things in a big way, but unfortunately we did not get much funding for that initially when I joined IISER. So I have also a parallel scheme in chemistry. So we currently do mainly on supramolecular chemistry, which of course has some relation to biology, but more towards materials. We make materials for various purposes actually. Still, I have interest in chemical biology, addressing cell signaling and all those things.
The younger generation has been part of brain drain with many leaving for better opportunities. How do we tackle this challenge?
Yeah, I think we have to increase the infrastructure here because science is global. Science has no geopolitical boundaries. So wherever you can do better science, that's where people want to be there, the younger generation. So, for example, in the US or other developed countries, you can do better research, you have better support, better infrastructure. And for example, I am competing with the rest of the person in everywhere actually, worldwide. What I can do here can be done n times elsewhere actually. So that's a fact. What we can do is we have to improve the infrastructure And we have to also increase the number of opportunities actually. For every country, there is something called per million, how many researchers are there. So that decides a country's prospects in some sense in years to come. Our researchers per million is 260 actually. And other countries, for example, China is about 2,700 or so. America and other countries are close to 6,000. If you're in science, it will take at least a PhD. So it will be almost 30-35 years by the time you settle. And for the other streams like IT or other engineering, one can settle in 25 or so. So that's why people usually go. And those who are really interested in science only should come. If people want money, we have to increase money in science, even for the salary, I think.
Tell us a little more about your areas of interest in science and about the patents you hold and the research you've been doing.
Currently, I work on supramolecular chemistry mainly. So in that, we make gels, for example, materials which can separate oil from water. There is a big issue of marine oil spill. Country which has a marine border, there is always a risk actually. Volcanic eruption or a ship collision or something can happen, and also rig accidents can happen, and it can spew tons of crude oil to the sea, which is very bad for the organism and also for the economy, because the current solution is just to burn it away. We cannot get that oil which is in water. So we have developed a material which can absorb only oil from water surface, and by squeezing that we can get the oil out. So we are cleaning the environment and also we are recycling that. So
are you putting it to use commercially? I mean,
we have done on a very small scale, lab scale. Now our next level is to make it to a larger scale, make larger material, larger sorbent, and try in real sea scenario. That we are currently doing. Also, we work on crystalline polymers. Some of the polymers we have developed are collagen mimic. Collagen is our body's protein which gives the strength for our muscles. Also, we have a lot of collagen in our bones. So if there is a fracture, we can make some material which is mimic of a collagen. So we have made several collagen mimics using our chemistry. Essentially a polymer of peptides. Collagen has 3 amino acids which repeats actually. So proline is one of the major amino acids, then glycine, then other amino acids also. So we have made this monomer using proline, glycine and other amino acids, and we have polymerized that, and we have tested their property as collagen mimic, and we found yes, they are really collagen mimics. Currently we are in collaboration with Sri Chitra Tirunal Institute to make a bond replacement using this material. We have published this research. Further work on application is going on.
What about IISER as an institute? How has it been doing? What are the key areas where IISER focuses?
It's mainly for science, include research at the very early stage. From BSc, normally we don't have research in colleges. So to have a better perspective for students, we should incorporate research also along with the studies during the BSc term onwards. So this is the concept of IISER. Actually, research also integrated into the theory studies. It is to attract students for science because we have several IITs. IITs are mainly for technology, BTech or BE, engineering related activities. There is only one IISc, Bangalore. So to address this one, we need more science institutes which supports research also. That's why our government has started IISER, and it's doing really well actually.
After our independence, when we invested a lot in science during that period, especially in space science and many areas, we have done exceedingly well. What do you think, how much money has to be invested, as a percentage of say GDP or whatever, for science to flourish in India?
I think at least it has to be 2.5% of GDP would be really good. This is what other countries have done, the highly performing countries in terms of science. We are still at 0.64, which is not that good. We are in our Amrit Kal or demographic dividend period until 2055 or 56, and we started this period in 2005. And this is the time we should have an explosive growth in all fronts, including science. And this is the time we should invest in science in terms of the funding and also in terms of personnel actually.
In your opinion, how much do we as a society value science and say scientific inquiry in India?
Unfortunately, we are not doing that great in terms of scientific temper. We are, very superstitious. We often follow pseudoscience. This is a sad reality. But people appreciate science. People enjoy the fruits of science. People have mobile phone. People have radio. People have everything. But there is a disconnect between science and common man. I think scientists should go to people and make them understand how science is important, what is science and what is not a science. And I think that should be done.
Many scientists we've seen are probably not as good, as communicators, but especially when you invest funds for research, people will certainly ask, where are the returns going to come from? So how do we manage this?
Government knows the doctor because they meet every day or often. But scientists, they don't know because the product they use through doctor is also a scientist discovery, or the mobile phone they use is also a scientist discovery. But there is a disconnect actually. So the scientists have to go to the lowest level and talk to people. This is the only solution. So it will take time. But we should communicate to the common man and make them understand this.
Currently, see, climate change, poverty, population explosion, these are certain problems that societies face. And how can science help solve such problems, which are closely linked to well-being of society?
Many researches are happening to protect the environment. Even my own research for the cleaning of oil from water. That is one example. And also many people are working on carbon dioxide fixation to make value-added products like methanol and formic acid, etc. Our agriculture started producing more yield because of fertilizers. People have ammonia discovery through a Haber process. There is nothing other than chemicals in this whole world. There is already a challenge by Royal Society of Chemistry. If someone brings any material which doesn't have a chemical or any chemical constituent, they will give 10 million pounds or so as a prize money. That challenge is going on for years and no one came with any material. We don't live anymore in the caves. Now we have better facility. We don't use bullock cart. We use cars. We started flying. We have better house. 100 years ago, average life expectancy in India was 24 years old. Now in India it is 70 and global average is 73. So last 100 years there is an increase in the life expectancy. That's because of various science actually, especially drugs and medicine, for example. Science is the one which makes us go forward actually.
I read that you had a role in synthesizing a drug for TB. Now how did this come about?
There was a global challenge to all scientists actually by Global TB Alliance and Rockefeller Foundation developing PA824. PA824 is a known drug actually, so it was synthesized by someone else and they know that it is resistant against even multiple drug resistant TB. So it can be used curing multiple drug resistant TB also. The problem was the synthesis, they started from dinitroimidazole, which is an explosive. So that means you cannot have a large scale synthesis. When you make large scale, this will explode. And also it takes 8 continuous steps and number of steps means the cost also increases. So this foundation wanted to reduce the number of steps and also they did not want to start from dinitroimidazole, which is an explosive. It was only a theoretical challenge and my suggestion was only a theoretical suggestion. So I have suggested a scheme which we started from chloronitroimidazole, which is not an explosive, and we have shown that it can be made in 4 steps. And that is how now it is being made globally, and it is an approved drug. Pritomanid is the name. PA824 is the initial compound name.
The other area that you often talk about is click chemistry. What is this?
Normal chemistry produces a lot of waste products. This was Sharpless in early 2000. He mooted this idea. There should be some reaction which doesn't make any waste. So this is that kind of chemistry which does not produce any waste material and it doesn't require any harmful solvents. It can react in water. It doesn't require harsh conditions like high temperature. So such a reaction which works under very normal condition without producing any waste. These reactions are generally called click reaction. For making drug molecules, you can use click chemistry to make millions of chemical molecules which can serve as compounds for screening for various drugs actually.
For all the listeners of Akashvani, I would like to thank you, Dr. Kana Sureshan, for the enlightening chat.
Thank you very much. Thank you.
That was Dr. Kana M Sureshan, a brilliant mind shaping our future.